Thank you very much for the very nice introduction. Now, this is actually both particle physics and photon science. Photon science becomes more and more important, and I will show you a few examples why and what we talk about when we talk about photon science. So my title of my talk is Pathway from Particles to Light. Let me start talking about light. Who of you likes light? Okay, so now counter probe. Who likes the dark? So everybody, it's not working. So some people don't like either the light or the dark. So I wonder. Okay, so light is very popular, of course, and I'll tell you why. And also the UNESCO has recognized that. That's why with international organizations, they declared 2015 as the International Year of Light. And light can be visible, can be invisible, and there has been a tremendous success story of producing different kinds of light. You all know the fire, the candle, which by 1879 has been complemented or replaced by the electric bulb. Photons have been described, then lasers, synchrotron radiation, the blue LED, X-ray, FEL. All these are ways to generate light, different ways of light, which have a very profound impact on our life, on all of our lives. And just 2014 was not the official year of light, but still there were 2 Nobel Prizes, one in physics, one in chemistry, both related to light. Again, the invention of the blue LEDs and a special kind of microscopy which beats diffraction. So light is very important. Why do we like light? Of course, because we see things, because we have eyes, I think. If we wouldn't have eyes, probably we wouldn't like light. Once we have seen things, we wonder what else is around. So humans have the dream to make invisible things visible, to see things that we didn't see before. Either by taking a ship, go someplace, see new things, or by, if you give something to a baby will take the toy and will try to break it down. Will look what's inside. Sometimes it's quite useful, like if you have one of these surprise eggs, you find some nice toy inside, and this is what physicists essentially do. We break down things, we look inside, what can we see, what can we find of new, exciting things, and for this we need light, and the birth of all of this started in the 17th century, when the microscope actually was invented, and this was the first time invisible things were made visible. These kind of microscopes, and accelerators are nothing else than big and very complex microscopes, depend on the quality of lenses, amount of light through optical aperture, like everybody who takes a photo will clearly know about this effect. And immediately, or some years later, the bacteria, for example, were discovered, and this is where medicine, for example, understanding of diseases and so on, took their beginning. First you invent the tool, and then you understand how things work, and you make lives better. Now, this made another huge step forward by the invention of X-rays, and you heard several examples about this already. Now you can look even into the molecular structure. The wavelength is pretty small, 0.1 nanometer. Your hair is typically 30 micron. So 30 or even 300,000 times larger than what you can resolve now. A hair is huge. It's a mountain compared to what you resolve now. And again, there are key challenges, but a big step forward for science and for our understanding of what we have around us. Now, this opened the gate to the nanocosmos, and we already heard examples about that. Now, if you want, you can describe the century we have behind us in some sense as century of crystals. There have been many crystals explored, and very useful things came out of that, so we don't only understand, we use it to engineer our world, to make it a better place, to solve problems. Superconductors, for example, the Large Hadron Collider you heard about, would not exist without the understanding and the manufacturing and investigation of superconductors. Super alloys, like your phone, is pretty insensitive against scratches on its surface, if it's a decent quality, of course. Now, this comes out of new materials, IT technology, very tiny phones, for example, high-tech magnets that have many applications in our society. So if you look in a, of course, very sunny day in Germany, I'm afraid it's not always that sunny. It looks pretty familiar in Liverpool. Now, if you look at a picture like that, you should see, okay, nice bunch of guys enjoying the day in the sun and having a chat, having coffee, and so on. But there's a huge amount of technology inside this, which was only made possible by investigating the world we live in, materials, solving problems. And I don't want to go through in detail, but some guy, he wouldn't stand there without his artificial hip, maybe. He would lay at home and wonder if there isn't a solution to get a new hip. Glasses, of course, protect us against the sun, so we can go to high mountains. Digital cameras allow us to keep our memories, exact time, intelligent credit cards, so soon you don't have to pass it through any machine anymore. It will just book the money from your account. You just have to worry you still have money on your account. So all of this is a huge impact on everybody's life. And as this symposium is called For Science and Society, it's clear we work on these little gadgets and we have a lot of fun on that, enjoying inventing new things, building new things. But then the society really profits from the things that come out of this. And such, the title of the symposium is very well selected, I think, and we can prove in many instances that there's really a huge impact on society. Most people don't know about it, but they should realize that this science is making our lives better. Now, the new challenge, now in more technical terms, essentially in the 19th century, we looked into continuous systems like a flame, water, whatever, thermodynamics, electrodynamics, mechanics. The 20th century, we looked at granular systems, so we understand atoms, molecules, fluctuations, quantum mechanics, X-rays as a very important tool to understand that. And we believe, many of us, that the 21st century will be the time of complex systems, where essentially we don't only understand, but we have quantum control of matter and energy, so we control to even higher levels. We design things. For example, some people wonder, why can't we build artificial photosynthesis? Wouldn't it be great? We have some plant growing out that gives us some hydrogen out of sunlight, and we fuel it with our cars. Now, this requires really very precise control on this process, understanding and manipulation. And we also need to know not only a static view, a picture, we have to have access to the time domain, so we have to understand how things work through the whole process of things. So the X-ray challenge of the 21st century, where DESY is involved and many other labs around the globe, is essentially bringing us from this era of crystalline matter into the era of complex matter, where things are moving. You don't have a static picture of a molecule, we saw that before, or bacteria, or a virus. We now look at the time evolution of things in an even better way. Now, and you see here that how do we do that? How do we achieve our goals? And we started with lab-based X-ray sources. The next was synchrotron radiation. And now we are moving towards X-ray lasers and high brilliance synchrotron radiation sources. Now, looks nice, but what does it mean here? These are all accelerators. So we move to something where accelerators are big tools, and we work on state-of-the-art accelerators for best light possible. I will not present you what I'm also deeply involved in, new accelerators, 10 times smaller, 10 times cheaper, 10 times better, plasmas and whatever. This is what we are dreaming. I will present to you what we have and what is already very useful. Victor Malka will go then into our future dreams and why we believe there's a big, bright future still for us. Now, what is a synchrotron? Actually, if you wonder why it's called synchrotron radiation, this light was named after an accelerator. The synchrotron essentially is a circular accelerator where we send some electrons in. A beam of electrons means some bunch of electrons, maybe a few billion, sometimes only a few million, sometimes more than a few billion. We group them together and we send them in forward, accelerate them, and send them somewhere. Now, in this case, we send these electrons into the synchrotron. What will happen is they will circulate, they can be stored, we can keep them for days or hours, whatever we want. Now, this must be a vacuum, otherwise the air would stop these electrons. We need something to pump energy into these electrons to make them high energy. These are what we call RF cavities. These are longitudinal electrical fields. If you remember your Lorentz force, then you can only accelerate with longitudinal fields. And they don't go by themselves in a circle, so we need something to bend them, and we bend them with vertical magnetic fields. If you remember from school, you have the three-finger rule, so where the field is, where the particle goes, and how it's deflected for a given charge. And this essentially, this formula, the only formula I shows you that you have a particle with a momentum p, the electron. If you want to force it on a circle r, the charge is given, of course, you need a field B. Now, it means if you increase the momentum, so put more energy into the particle, the radius should stay constant, otherwise you build a big accelerator, you don't want that. So you have to increase the magnetic field. And this is where the name comes from. So increasing the energy of the particle, you have to increase the field of the magnets at the same time, synchronously. Because you have to do this synchronously, this is where the name synchrotron comes from. And this is essentially explaining in a minute why we call it synchrotron radiation. Now, this particle goes in a circle. The situation in 1946 was like that. Accelerators were still quite tabletop, quite small. This is a glass vacuum chamber. You might have seen on the posters many metal accelerators, metallic pipes. These guys started off in this accelerator with a glass thing, and then you can guess where would the particles go here, the electrons. They would go in here and circle around. Of course, not with a guy standing by, because this is a little bit unhealthy environment. So they knew that at the time. The synchrotron, as I said, can store beams a long time. So what happened? They built a thing like that. Then it looked like this. You need magnets around, cavity, RF fields, etc. So, and this pipe is somewhere in there. And then suddenly they set all behind a wall and saw some sparking from one of the pulse transformers, they thought. So what happens? All the scientists stayed outside, asked a technician, can you have a look inside? This guy was called Haber. And he went in, he looked around the corner of the wall. Okay, who cares about radiation? And he noticed a very bright spot, and he even took a photo of light coming out from the tube on the left-hand side. That's the first time you've discovered this synchrotron light. And it's called synchrotron light because this is a synchrotron accelerator. Now, and Pollock, the scientist in charge, he then speculated if a prior accelerator, actually a Betatron accelerator, which was built before, which if that had a glass vacuum chamber, synchrotron radiation would nowadays be called Betatron radiation. Now, and this immediately sparked interest. These times were still different. So what happened? Immediately after the discovery, 1947, the academic community, of course, went there. You're not surprised. Everybody wants to see what's going on, a new kind of light, synchrotron radiation, what is that? So they had 6 Nobel Prize winners going there. Okay, you say, that's good. That's their job. Nobel Prize winner, he must follow up on new ideas. What was amazing to me is that also this guy came. This is one of the most famous spies, Klaus Fuchs, who worked in the US and helped the Russians to develop the nuclear bomb. He was a spy, and before he was caught, he also went there. See what's up with synchrotron radiation. Funny, nobody remembered his visit. So this was such a good spy. He visited the lab, and you didn't even see him. But FBI proved that he was there. And the last guy, of course, if you're a good actor and politician, you always also want to be on the top of the scientific developments at these times. Ronald Reagan went there for 20 minutes, way before he became president, and also visited the synchrotron radiation. So apparently, a big impact on society was obviously immediately expected. Now, it took another 30 years until it really had a lot of benefit, and it was shown by Graham that the first operational facility was in the UK exploiting the benefits. The accelerator physicists were using it for steering the beam, for optimizing the accelerator. The scientific usage was only coming 20, 30 years after. Something we always ask, what is the thing good for you build? Sometimes you have to wait 20 years or 30 years until it really revolutionizes the world. So again, you have an electron, it gets bent. When it gets bent, it sends a photon. So what happens? The photon carries away some energy, and the electron energy is reduced. So synchrotron radiation essentially means you convert energy of electrons into photons. That's why we like our electron accelerators. We can generate a lot of good light from these things. Just through this physics process, it's like you go around a corner with your bike. You start braking. If you brake, you have to send the energy off. And you send it, your brakes normally, not into light, only if you fall down. You get some sparks. Here, it's sent off in lights. Now, we talk about relativistic electrons. So electrons with light velocity, they must be fast. Otherwise, they would radiate in all directions. You might wonder, why don't they send in all directions? We want a forward cone. So this is very important. So we have to have high velocity, and this makes accelerators a little bit larger. Now, then you wonder, it's bad that it's emitted all around the ring. So you make a ring which actually have little radiation in these arcs. There's still radiation. And then you put something we call an undulator. And this is an element with up and down magnetic fields. And this actually wiggles the electron around with a much more curvature in the system. And then here you radiate in this undulator. So the undulator brings up the charge a lot. So we get more photons because it wiggles a lot here. We have localized emission areas, and we get a well-defined photon beam. And this is very important to put it to some place, where we have, for example, our superconductor or biological sample when it arrives there. And you see the benefit immediately. I told you about before that these bending magnets, just to turn them into circles, generate something like that. And now you see with these called undulators, this trick, we gain 4 to 5 orders of magnitude in number of photons, and this is a big step forward. That's why, if you ever visit a facility like that, you will see undulators. And these are the synchrotron facilities we have at DESY. You see these electrons circling around, these photon lines delivering to many, many users. And of course, there are other big facilities like Diamond here in the UK and all around the planet. This is really, they grow like mushrooms with so many customers. And something new is this NanoLab. We really try to focus more on the nano materials and nano processes. So with modern X-ray technology, let's look at this Petra big accelerator ring, the big one here, 6 giga-electron volts. We do tomography, diffraction, fluorescence. Sounds good, you might think, complicated, maybe boring. What it means in real life is we look at health, IT, renewable energy, transport. This is where the users come from, and they exploit these photons and this light for making progress in their fields. Now, it even affects art in a way that you can put a Van Gogh, Grasgrund 1887, into the light, and probably he had to save money, so he used his I don't know how to call it in English, painting ground several times, because if you radiate it, what came out and investigate, some people had suspicions, you find another painting below. And this is something, making the invisible visible, is something that was done now for several paintings and really allows us even to understand art history and the history of painting better than before. Probably didn't like this picture, I guess, and put the grass above it. Maybe it was one of his enemies, I don't know. You speculate. Okay, expedition in the nano world. This is what is very important for us, where we are embarking. Besides doing particle physics, we are strengthening this path. Nanomaterials under real conditions, internal molecular structure, nano diffraction, all very nice and cool things one is doing. If you talk about careers, perspectives, all of these guys make very nice careers who look into this very modern ways, things, problems of physics, biology, chemistry, etc. Now, what about, because laser, what about a free electron laser? Now, free electron, what does it mean? free electrons is our beams of electrons. So this means electron not in an atom, I guess. Not bound in an atom, in a molecule. That's why we talk about free electrons. Very simple. So you immediately understand free electron laser. Now, laser, what is a laser? A laser is actually done by exciting electrons in an atom to higher energy states, and while it decays again, goes down, you emit photons. And by putting this process between two mirrors, you can have stimulated emission, which means the photons act on this process, and in the end you get a forward beam, because this thing of course radiates in all directions. Under the influence of the photons bouncing back and forth on the mirrors, it goes forward into one direction. You have stimulated emission. This is what a laser is. Now if you want to build a free electron laser, okay, we understand free electrons, we take our beam. They are not in an atom or molecule, so great. But how do we build a laser? The first kind of laser I want to show you, because it looks similar, remember this is how it looks like in a traditional laser, like this one here. I hold it in my hand. Now we can build it in a storage ring, sending the particles through an undulator. It radiates photons back and forth, and this radiation of photons is affected by the photons bouncing back and forth, and you get what we call a low-gain free electron laser based on a synchrotron. This requires optical resonators, mirrors, so it's done for FELs for infrared or visible light. It cannot be done for X-rays, because the X-ray photons will pass through the mirror. To get a few percent gain per passage, again, we use our undulators here. So you see, we have now built an FEL, just replacing the atom and the gain medium by our beam and the undulator. Now, this only works for lower wavelengths, for higher wavelengths. So now for X-ray, how can we do it? Now you can wonder, forget about the circular thing bouncing back and forth. It's boring, it's complicated. So why don't we send just the electrons through an undulator, very long undulator? They generate photons. But inside of this thing, the photons must interact with the electrons. So we send the electrons through. Each electron emits in here an electromagnetic field. And instead of coming again and again and again, we make this undulator long enough that these fields start acting on other electrons, establishing what we call a collective interaction, or even collective instability. So actually, instead of coming again and again, like in a normal laser, here we only go once. This beam then reacts, the electrons react to the light by forming microbunches. So our, let's say, hair or bubble of beam electrons goes sliced into very, very fine slices by this interaction. And what happens is that the radiation emitted by all these electrons in here becomes coherent, and the power scales with the number of electrons squared. So I told you let's say we put 100 million electrons. So we should be able to gain a factor 100 million in the radiation power. And this is shown in a now called flashed accelerator, where essentially you go along the undulator length, and then at some point you see exponential increase, and you gain 4 orders of magnitude until it starts leveling off. This is a free electron laser. So doing this thing in one go instead of multi-passage. And this was predicted, works very beautifully. The nice thing is you don't need mirrors. So now we can irradiate X-rays, and we don't have to bounce X-rays back and forth, which is very complicated or even impossible. So now we can get an X-ray free electron laser, which can have many, many applications for science and society in the context of this symposium. Now to visualize, if all these guys would kind of be unsynchronized and everybody has his own rhythm, his own clothing, his own look, they would not act as strongly as like that, where they really form a team and pedal coherently. And you see even the legs are coherently. Now, of course, they go much faster than a bunch of non-coherent guys, and this is actually what's exploited here, going coherently. The impact is, I showed you before, the power going from bending magnets, synchrotron radiation sources, goes now up to 10 to the 33, so 10 orders of magnitude to something where the XFEL will be sitting, or where the LCLS, the large linear coherent light source, at SLAC is sitting. They are already operating. The XFEL is something we are building at DESY, will be the largest and highest energy X-ray free electron lasers. We get many, many more photons. The other thing, because now the electrons are generating these X-ray pulses, we can have many electron pulses. We can slice them, micro-bunch them, whatever, put many bunches, and what we get is essentially not one photograph. We get photographs separated by 80 nanoseconds with a duration of 50 femtosecond, maybe even no smaller than 10 femtoseconds. So we do not just photograph the nanocosmos, we film it with a pretty good rate of pictures. And this is all possible by using electron beams instead of for example, continuous beams or whatever. There's a big advantage by, for example, of superconducting accelerators. That's why XFEL is superconducting, and SLAC is also moving towards superconducting, because then you can have many, many of these pulses, so you can make very long movies of what is happening in nature. So see, 10 billion time improvement. This is a big advance. So this kind of progress usually changes something. If you ever invent a technology that advances something by 1 billion, you should patent it. Now, so coming again to DESY in Hamburg, in the city, we have not only our storage rings, we also now have one operating X-ray free electron laser. I showed you the gain curve, this exponential takeoff and then saturation for this accelerator here. It has been extended just recently to satisfy more users. We have the problem that we can't satisfy all users, so this is expanding. And then what is being built right now is this European XFEL, which will be completed in a year or so. Now, Flash, of course, has already produced a lot of results. I don't go through the details here, but there are many users, multi-users. We can even satisfy soon more users than one. I just want to point out, of course, Germany is not everything. Europe is not everything. There are XFELs all around the world, in Asia, in Europe, and the United States. So also, if nobody embarks on the idea you have, something is wrong. So it's a good sign, and probably this will grow further. Now, the XFEL will look like this in 2016. You see the user building. Everything is underground, of course. So it goes from the city all the way to the countryside because it's so long. This is how it looks like in the tunnel at the moment. They install the main Linux section, and there have been whole module strings already been installed. So this is now going on with a lot of effort at DESY. So you might hear exciting news in some while about that. The killer application we think about Henry Chapman. He might be known also in the UK quite well. He is building femtosecond nanocrystallography. So you use 400 undulator, almost half a kilometer away, beryllium lenses, the action points, and film at 10 femtosecond what's going on in these samples. This is trying many of these methods from XFEL already at LCLS. So XFEL DESY scientists were leadingly involved in these studies. That is one example of where XFEL, the team at LCLS, disclosed the structure of an enzyme called sleeping sickness. So understanding this sleeping disease, of course, is very important to a lot of people who have it. You never know, maybe we get it. I hope not to my talk, though. Okay, so I must close to the end. We have several applications for free electron lasers, fundamental holy grails, applied science, biomedical applications, very important, and opportunities for industry. They are very interested in friction and wear. How do things rust, for example? Yeah. So, future looks bright. I can't tell you about our new ideas about accelerators. Many of you might know me now, as of the senior guys here, as an advanced accelerator guy. I spent most of my career on these conventional accelerators and still work on that. Now, of course, we have very nice ideas about novel accelerators that might also from the technological side change the way we do things, but Victor will give you much more details and details on that. So I will finish with that short overview about light. coming from accelerators and bringing us to the quantum cinema. Some really exciting movies. We will come to cinema hopefully in a few years. And I thank, of course, all the different persons who contributed, especially Helmut Dosch and his team. He's our director, who gave me quite a number of slides that I can present today. So thank you very much for your attention.